This is the only link that you need for what we're going to do, and I'm giving you the link right here. So that's an open link. You should be able to see it. And what is this? Because if you're, especially if you're new to this, then I'll tell you that it all started when I first learned about quantum computing. Yes, there was a time when I didn't know anything about quantum computing. And I taught a class at Cisco. So that class, I'll have to talk about it with the leader, with the chief of education at Cisco, because some students were excited to know no limit, and some were just the opposite and gave it a 2. And I think I know full well why is that. That is because they expected that I will teach them a new programming language called quantum computing language. And what it turned out is that this is the future. Right now, there is no application that is better on quantum computing. So number one, I taught them how to repair a time machine, and there are no time machines around. And number two is that they thought to learn a computing language, and it's not that. It's a future that you really need to learn about, and learning about it turned very hard. So that was the story. And I see, let's see, let me look at the participants because we're starting. Okay. It must be I'm not very popular because we have only 2 people. Or let's put it another way. Quantum computing is super important. That's what I'll be talking to this company about today. But it's not for everybody. It doesn't bring you money today. No serious money. And you have a PhD to have a PhD in computer science. But it's extremely important, extremely exciting. And, you know, China is rushing ahead with quantum computing. And there is a picture of President Biden, like, let's see, there is this picture. There you are. So the president is looking at the quantum computing. That's very cool. But many more people are interested in what is the president saying about canceling student debt than this. So we don't get much popularity. That's okay. Let's keep working on this. Now, every time what I do is this. I tell you what I'm going to do. We have about an hour, maybe a little less. And I will tell you this. I will look at the news. I will also look at one of the labs of quantum computing. What's the state of those labs? Because that's practical. And let's start. So when we were partying last Friday, somebody asked a question, and he said, okay, I know machine learning and I know Python. Do I know quantum computing? And I said, let's not try to guess. Let's just go to ChatGPT and let us get its answer. So we didn't have the time to read about this. And I'm opening that right here, right now. And no, I really want to open it. Why didn't it open right here? Wants to open another tab. Okay, fine. So it says when you're programming machine learning using Python, you use the same libraries. It is the same knowledge, but it works on completely different objects. Now, he lists which libraries you use and talks about quantum machine learning. That is, by the way, my next webinar. When I finish this one, I'll go and do the AI webinar. It's right here. You're welcome to come. But in quantum computing, you use the same language. Yes, you use Python, but what you do is completely different. That's what he tells you. So to me, that doesn't explain things very much. So we'll try to discuss them. But he says that you use Python library, which I'll show you today, that allows you to operate on quantum bits. So we all know there are bits inside of the computer, a classical computer, but there are quantum bits inside of a quantum computer. So that picture that I was showing you, just this one, really shows just the wiring. So that those wonderful golden things, they all wires. But the real quantum computers, quantum bits, they are deep inside, probably here, maybe. That's the wire that you need to connect every bit to every other bit. But the chip is pretty small. Quantum chip is, let's look at quantum chip. Chip. Again, pictures. No, not news, but pictures. Yeah, there you are. So quantum chips are pretty small, and we'll talk about how small. What they have inside are quantum bits implemented as, and that's a big question, what really is the implementation medium for that? Then he mentions, so maybe it's electrons if you are managing to do this. Maybe it is photons. So each little photon can be a bit, a quantum bit. So why would you use that? You use that instead of regular bits? That is because this special quantum bit can be in state 0, it can be state 1, but it also can be in every state in between. Now, tell me if that's the first time you heard such a thing. Okay, I'm opening the chat and I'm closing this. So I'm opening the chat. Where is it? Here. First time. Just say yes or no, because I need to know if you know. First time you heard about this or not the first time? Nice, I need to know. No, it's the first time, very nice. So I won't expand on that. Very good. So then you know what quantum computing is all about, and you're interested in some more information. So first, let's look at what are the latest news. I found two interesting news. First of all, that potentially people are looking at room temperature quantum computer. That one which I showed you, that one which President Biden was looking at, it is working under very cool temperatures, cooler than the outer space, and they had to warm it up before opening it. But it's a well-known thing. But it turns out you could do this. You could do room temperature quantum computers. And what you will get inside are photons. So whenever you talk about quantum computing and you are mentioning, well, I don't know what it is implemented as, then today you can really talk about photons, and they're polarized, and all the physics that you learned becomes real. And the only thing is that I couldn't figure out right away how close it is to reality. They say that it is good, that it is a research, and research by whom? I think by some university. Very latest news. I am a member of the Quantum Computing Qiskit Slack, and I asked guys, how real is that? What do you think? And didn't get any reply. Sometimes I get nice replies, but this time I didn't. So my idea is that it's nice to know that such things are possible, but I don't feel that we have to worry about this. Besides, who is going to make those computers? That's either IBM or Google, or I think it's Rigetti, one of the three. And whatever they do is fine because we operate on the level of Python code, Qiskit library, talking to quantum computer. Not necessarily Qiskit, that's the IBM development. Google has their own language and it's similar. I looked at it quickly, it is similar to the Qiskit, so it's okay, I think, to concentrate on Qiskit. That is one piece of news. The other piece of news is that potentially they can observe this wonderful Schrödinger cat that is either dead or alive, and they're getting closer to real life. Because up until now, you would answer anybody who asks you the question, how crazy are you? Do you really love cats? And all of that, you would say, well, don't worry, I'm really not talking about cats. I'm only talking about photons or ions. But this paper says that you can go much, much higher in size. That's not still on the level of cats, kittens, and lions, but it is, I think, the idea, and you can click here and get the real paper, and then on. I should really put it PDF download, but I should drop this PDF in the folder. By the way, whatever material I mention, I usually do drop in the folder. This is our folder. Here it is. And I will drop it in the folder. Yeah. Right. We just downloaded it. So let's say big size qubits. So how big size is big size? I think they mention microns. So it's not completely big size, but it's not your previous. It doesn't want to do it. Okay, upload. Here. So next time you look at it, you'll see that. These are the most interesting news. If you have anything else that you want to share, you're very welcome. But we'll go back to our webinar outline. And what I do then is a little lab. So as you probably know, you program those quantum computers with Python library, Qiskit or otherwise. So let's open the terminal. Let's make it big enough. And what I want to do now is just look at one of the labs and talk about quantum computing, because looking at the real code and the real labs, we'll be able to do something. Now, in my case, I have it in projects in quantum computing, I think. Oh. Okay, City Quantum Computing Labs. And now I need to be in the right Python environment. So I'm saying conda activate, and I have prepared an environment for quantum computing, and I called it Qiskit, I think. That's the environment. So that has the right libraries. I don't know how to verify what is in your environment. One command, I don't know. But it would be in the setup lab. So I will first start, and then I will tell you how did I come up with this. So I'm saying Jupyter lab. And once I said this, it starts up Jupyter lab in the right directory. And here are my labs. So I haven't closed it. It's available to you guys. And if you want to, let's go up. That's what is included right now. It's an open lab because the truth is that I'm copying it from IBM. But on IBM, it often doesn't work. We'll talk about this. So what you get is this is the setup. And if you want to set up your environment, it tells you how to install and how to prepare. But that is there, and the labs are mentioned in the quantum computing webinar. So if you want to know where the labs are, it's here. Okay, what I'm showing you now is the labs themselves. So let's go into the first lab that's talking about quantum computation. And I thought that maybe people don't have exact experience on this. I see this, somebody says something, but I don't exactly know what that is. So Bogdan says, gives me the link. If I click on this link, okay, so he gives me the link at this, or somebody else who joined. Let's check who joined. Wow, guys, I'm talking thinking I'm the only one here, but that's not true. I have Kenneth and Joanne and Lawrence, and that's great. Thank you for coming. And I gave you all permission to talk. And please speak up, because then I know that you are speaking as opposed to chat when I don't know that you are chatting. Okay, so let's go back just a little bit, and I will tell you what we've done so far for those people who are joining a little bit later. That is the link. When somebody, I remember, asked a question last Friday, he said if he knows Python and machine learning, does he know quantum computing? And ChatGPT answered. So if you click here, it will tell you that, Python and machine learning is great, uses one set of libraries, but quantum computing uses another set of libraries. So technically you are close. But of course, this futuristic technology is completely different from no less exciting ChatGPT. And that's what we're doing. A couple items of newsworthiness was that, first of all, we're getting close to room temperature quantum computers. So those of us who design quantum computers will not have to, freeze their bottom out. And the second is that you can demonstrate it to your mother-in-law, sorry for the joke, by showing a 16 microgram mechanical oscillator that works on the principles quantum physics, but that is much bigger than the photons or some other particles that you use as quantum bits. And now this is, let's look at a lab. Now, if I am nice, then I should really put it as a link. I'm saying this is where the labs are. That particular lab is open, and it's quantum computing lab. And I have something in mind, very specific. Here we are, and I want to do the very first lab, and I want to give you a link. So because this is GitHub, it shows Python notebooks as they are. Very nice. And I'm picking up this link, and I'm putting it here for future users of people who want to come later, and they want to see what is it that we were doing. And here's the link. So now it's alive. Now I opened this lab. I showed that here we are going to the right environment and getting some errors, but they don't stop us from working. That is the notebook. And last time when we were talking last Friday, I realized that maybe we're talking theory too much, and we never did or recently did not do enough labs. And that's what I prepared for you. At least the start of this lab. That's what I want to do now. And let's do this. So we said that quantum computers are based on amazing things called quantum bits, qubits. And the special quality of these qubits are that they can be either 0 or 1, but when you don't look, they can be anywhere in between. Well, that's physics. That's an interesting thing to think about physics, and we'll give it a thought at the end of this chat today. But practically, you need to assemble. When you go to quantum computing, you need to create your quantum computer. The first thing that you do is you create a circuit. So many people are taken by surprise that there is no such thing as quantum computer. Yes, there is, but when you are solving a problem, you will have to create another little quantum computer. You need to create a circuit, a quantum circuit inside of your quantum computer. And we were looking at the picture of the president with quantum computer, right? So we were looking at that. Impressive picture, of course. And we said that all these goals are connections between photons, let's say, or between IBM, I think, is using ions or something like that. So these are the connections. And that's what you need to build. You need to say this qubit will connect to this qubit. Then you send it to IBM for execution, or you use an emulator of your quantum computing problem. But please argue with me, comment on what I say. Okay, here we go. So what you do is, okay, you need to create a quantum network. Well, it will be something like that, but except that it will be really created by you. Then when you want to use it for any purpose, you will do the emulator. Here will be at the emulator. Now, I'm jumping, but then I'll go, just because I want to show you the final result first, where we're going with this. And then I'll go back to the beginning and we'll do it again. And this is the emulator that I wanted to show you. I wanted to say this is the air emulator, and I imagine that, you know, 4 things on which the world is built are air, earth, and fire. So that is this emulator. With that, I want to go a little bit to the state of quantum computing labs. So when I started preparing this class and this lab, then I discovered that IBM has a wonderful Qiskit manual. If you look for IBM Qiskit manual, IBM Qiskit textbook, maybe like this, resume your journey. Qiskit textbooks. Then at this time, they had a previous version of that. But just as I was teaching my first course, at this time, they switched. It was April 11. I remember it all too well because my class was April 11 and 12. And we used a little bit of this one. But since they were changing, we fell back on my own. My own is found right here, and that is the link to the lab that I show you. So amazingly enough, my programming habits helped because I looked at the previous version when it was available, and I downloaded the notebooks, the Python notebooks, because behind everything is a notebook, and at this time it was available. Then it was an improvement, supposed improvement, and it would only run, and that other notebook would allow you to run at IBM's expense. It was running on IBM servers. Of course, when you run it for who knows how many thousands or millions of people, something might break. It's different from me running it here. Is my server, right? And I run it. I'm in control. I have it on GitHub. So supposedly it was an improvement, and I apologize if I missed something, but I think they removed the runtime. So now you can browse the content. Yes, you can browse the content, and you can go anywhere. Let's go anywhere. Single systems. Okay, and it's a wonderful textbook. Wonderful textbook. So let's go to pretty much the same lab that I'm going to do. So let's give them a chance. Let's open another lab. Here we are. Well, it's wonderful, scary math, but that's a quiz. Very good. But where's the code? Circuit sandbox. Okay, there is the code. Can you run it here? I think you can. Yes, wonderful. Okay, I take it back. It is not worth, but still, I feel very safe having all my code in my place where I can run it, because that, when you're in class, is not guaranteed to run. But in any case, we found the lab, and we're going back to my lab. Now somebody says something. Qiskit.org, thank you, Jan. But back. So I'm getting their labs, but I'm making sure that they run. Here, run them on my server, and everybody who wants to repeat what I'm doing can go to the setup. Here, that's on GitHub, and being on GitHub, you can go to the first set where I tell you how I prepared the environment and how I'm running in the environment here called Qiskit. So I install Conda and then created the Qiskit environment in Conda. And everything you see, I'm in Qiskit environment in Conda. And now I can show you the lab. I will still work with IBM provided tutorials, but I will also maintain my own, because then you don't depend on wonderful corporate launches, and you show it. Now, that was an introduction. Now I want to briefly show you the lab and get you interested enough so you would have an incentive to really go and do it. Now, in this series of labs, we will do what is called atoms of computations. So in classical computers, atoms of computation are bits. But of course, after the bits, you get the assembly, and then you get the compiler, and it's many layers. With quantum computing, you have to go back to layer number 1, qubits. But that will give you amazing power, because every qubit can be in very many different states. And the secret is just to tell it the rules, how to go from one state to the other. So I'll assume that you attended half of our talks. So some things you know, some things you don't, and I'll continue from there. And as a general outline, you first build your own network, something like that. And that is built with the help of a quantum computer. And here we have 8 quantum bits here. And then you tell them what to do. In this case, what you do is print, not exactly, you say measure. And that measurement now goes and it is put into the regular bits. So you probably created a network that has 8 qubits and 8 bits, and now you can output it. Now, in quantum computing, it's a little bit different from the regular one. The regular one does the computation just once. The quantum computer is never sure. Its humble posture is that it can make a mistake anytime. And that's because we are so little, we're on the level of so small a particle that any kind of interaction with the outside world will mess up the results. And therefore, by default, it runs every calculation 1,024 times. You can change that number and you can run the calculation a different number of times, but then it displays what it got. Like here, it says, I ran it 320 times. Where did it get 300? Well, 300 times right here. If you say shots 300, that's what we did the last time. And we ran it for only that much. And then it says, well, and all the time that I did, I got 0. Why did it get 0? And by the way, 8 zeros you got. That's because here you created 8 qubits, didn't do anything to them, measured them, and you got 8 zeros. Still, these were qubits, and they could have made mistakes and interferences, right? So the reason why this had no mistakes was because we used a simulator, and the simulator, at least default, doesn't make any mistakes. I'm not sure if they would implement errors in the simulator because who needs that? But in the real computer, we could get different results, and the real results usually come back like this. So now let me do this. Let me go back and show you how you run this. Now, if you're familiar with notebooks, you know you can run them by clicking on Run, or you can run them by doing Shift Enter. I'll be clicking on Run just so that you see what I'm doing. So that's an introduction to the lab, and it is also a textbook. So you're going through the textbook as you are executing the lab, and it's talking about quantum computing, how it's different, and how you take information and split it into bits, and then how you add the circuits and make them run. Okay, so here you are. When Python notebooks runs, it puts a little star here to show that it's busy, and then it executes, and if it gives you no errors, it works. So we first imported all of the needed libraries, and then we talked about, okay, this is a number. In decimal notations, it's represented as powers of 10. In binary notation, it is as powers of 2. So that is a binary notation that everybody knows. And therefore, you have a direct mapping between your number to your number in the 10 notation to the number in 2 power of 2 notation. It will be a little bit bigger, but it will still be a number. And then you can explain it to your quantum computer, where you say you bit number 0, you become 0. And you bit number 1, you become 1. And that's, 0. And that's no fun until you really say, but now be real. Go into this, what is the state called, right? The state when it can be anything between 0 and 1. Can anybody remind me? See? Superposition state, right? That we're not doing here. Here, all of our qubits are either 0 or 1, and we create a binary widget with that. And I'm executing it once again, even though that's a notebook that has all of the results. But to prove the fact that it really works, Now that is just a picture. That says doesn't matter what it is, but remember when you studied computer science, you had these kinds of circuits. Well, these are the same circuits that we're now implementing in quantum computing. So we're back to the level of just pure bits, but you have to accept it. You know, to me, it was a surprise, and maybe to some of the classical programmers, and as they call people with classical computers, maybe that was a surprise. So you take the qubit, then you apply a certain transformations. They're called gates. So each gate has a name, and that is just an example. And each of them really means something, but you don't have to remember what means what. That will come with the code. And then finally you say, now measure this bit and this measure that bit, qubit, and really put the result into bit 1, bit 2, or bit 0, bit 1. So we are doing the same thing that we just waved our hands and talked about, but now we're doing it for real. And we're saying, here is my quantum circuit with 8 qubits and 8 regular bits. By default, it will be the same number for the bits. And if I ask to measure them all and draw like this, it shows me 8 bits measured and they are zeros. Now, that picture was different. That's because it was in a different environment. There it looked more colorful. I don't know what's the difference in the environment, but I never investigated because the functionality is the same and the meaning is the same. So let's continue. We created a 8-bit circuit and we decided not to bother the real computer with that. We could. We have an environment, and that environment is pointed to real IBM computers. And here, instead of simulator, we could ask for a real IBM computer. When you do this, you don't have to worry about the charges. It's one way to put it. Another way is that you do have to worry about the charges, because depending upon the size of what you're doing, it will either charge you or no. In this case, it really won't charge you because it's only 8 qubits. That's nothing. But in real environment, you would switch that to a real computer, ask for the least basic computer, and some of our labs have that. If you look at your leisure, if you look at other labs, there are some real computer labs that are solving real problems. Even so, the biggest problem that was solved so far is 15, factoring 15 into 2 prime factors 3 and 5. That's all. And for that, you don't pay. So no worries about payment, but still we're polite. We don't want to bother the real computer, and we do the simulation that will remain here. I think it won't even go to IBM. When I submit real jobs, then I usually get in queue. How long is this queue? Well, in my experience, it's between 200 jobs to 1,000 jobs in front of me. Depends upon the day and time of the day. And it's fun. It may take an hour. That reminds you of IBM mainframes. Well, that's similar. The whole world is using their cloud. But here we are using the simulator. We say now it is a simple problem. Just set every qubit to 0 and print it. And that you can do. And that's what it does. And it tries 300 times, as I told you, and gets the same result every time. Now it plots. It says, that's what I got. Even that takes some time to calculate, but that's what I got. That's a histogram. And I got the same result here, 0. If that were something more realistic, I would display a result here and how many times you got it. Another result here and how many times you got it. And in the other labs, there is a similar thing. So what I suggest you do is one of the two things. Then we go into more complications, more interesting things. It got 1 and all zeros. So let's not worry about more complications. What you could practically do, if you have already done these labs, then it's just a discussion, nothing new for you. But if you have not done them, well, use this lab, download it, use the instructions here, the setup instructions. You will be able to set up your own labs. When you have any kind of problem, just send me an email. I'll help you. I hope I will be able to help you in setting things up. And then you can run. It turns out that you can run on IBM site. I just ran it. And I want to run another one. They start with something a bit more complex. It runs. As you can see, it is running right now. And that's why I don't like to run it on their side, because you get a big delay. On your own computer, it would be better. And of course, it doesn't do anything until it hasn't finished this one. So it's running here and it's waiting here. All right, that's what I wanted to show you. I wanted to do a quick overview of what's going on and the state of computation on Heathkit Labs. I showed it to you local, that's local running. I showed it to you on IBM, that's IBM running, and it worked perfectly as expected. Perfect means here, it promises, or I promise for it, that it may be hanging. Okay, and it does wonderfully well. What I can do is rerun this, and that doesn't help at all, which means I wanted to disconnect from the kernel and stop that, but you see, it doesn't allow me. It is still thinking or waiting, and that's why I'm back to my suggestion. Have your environment under your control. Okay, next time I will do essentially the same thing. I'll look at all of the news that occurred this week, and then I will do some other lab. That is the plan. So I can do it right away. I'll say that this is the plan for the next time. But I think I'm teaching on this 12, so it will be 9. Ian, okay. So first we'll look at the latest news. And then we'll run a lab. So these news will be different by then. And there will be a practical lab. Of course, news are to be determined. And practical lab is also to be determined. But we have a little time for a little philosophy. And the philosophy is very simple. When I talk to people about this, they do get struck by the amazement of this. ChatGPT is changing the world right now as we speak, but it's not as mystical state enforcing on you. So me in particular, I always wonder, why are all electrons the same? You know that all electrons are exactly the same, and not even that. They can only are allowed to say specific, to have specific states. How could it be? That is what I want to ask you. Now it seems like we don't have all that many people left. If I go to, no, we have everybody here, participants. So we are essentially done. Give me your reactions. Tell me what you'd like to hear next time. I will go to the chat. What would you like here about next time. Okay, here, next time. Okay, so just tell me if you don't have anything right now, you can always email Mark at Elephant Scale will work very well. elephantscale.com, but you'll figure that out. And that way we're giving a little problem to the bots. So everybody, thank you very much. It's great to talk to you next time. Go through the architecture, Lawrence. Okay, architecture of what? Architecture of the program, Python code, or architecture of the quantum computer? Of quantum computer. Isn't that wonderful? Okay. So news, yes. But then okay, wonderful. Thank you very much. Google Doc is right here. Copy.
Thanks, Mark. Have a great weekend, everyone. Thank you.
Thank you, everybody. Yes. Yes.
Bye-bye.
Goodbye, everybody. Have a great weekend. Goodbye. Thank you and goodbye.